Hello students, welcome to today's lecture of Theory of Automata and Formal Languages. Today we'll be discussing about how we can convert a given push-down automata to an equivalent context-free grammar. Okay, so these are the contents for today's lecture. We'll be giving some introduction about the push-down automata and the equivalence of push-down automata and context-free grammar. Then we'll be giving an algorithm to convert a given push-down automata and write the equivalent context-free grammar and implement that algorithm using an example. Okay, so see what push-down automata is. If there is a push-down automata given by these septuple, one is where Q is what? Q is nothing but Q is finite set of state. Q is your set of states of your push-down automata. Okay, sigma is your input alphabet. Sigma is your input alphabet, from where the symbol from the input alphabet. Okay, then your tau is your stack alphabet. Tau is your stack, you can say stack symbols. Delta is transition function. Okay, delta is transition function for your push down automata. Q naught is the initial state. Q naught is initial state. Z naught is initial stack symbol. Z naught is initial stack symbol. Okay, and in this case we have written phi over here, that because we are assuming for the sake of simplicity that your automata, push down automata is a you are accepting a string by the empty stack. Okay, so there is no final state in that case. So if A is a push down automata, then there exists a equivalent context free grammar G such that the language of grammar G is equal to the language which is recognized by this push down automata. Okay, so this is what we are going to achieve actually in today's lecture. Okay, so first we'll be seeing what is the algorithm to do this, and then we'll see what is the how we can implement that algorithm by taking an example, right? So PDA to CFG, the algorithm says that, see, when we are given a push down automata, it is there are states, there are transition function, there is a stack symbol, input alphabet, all those things are there. But when we convert this push down automata to equivalent context free grammar, then we actually give a context free grammar. Okay, and any grammar is defined by these four tuples. One is V, where V is the set of variables. This V is the set of variables of your grammar. This is your input alphabet. Okay, input alphabet. Sigma. P is production rules, set of production rules. Okay, P is set of production rules, and your S is your start symbol of your grammar. Okay, and S belongs to your V, it is a variable. Okay, so we actually, when we start converting a push down automata to equivalent CFG, what we have to do is we define a grammar G, V, sigma, input alphabet, production rules, and S, and then we'll define what are the variables in our grammar one by one. See, V is the variable, set of variables for our grammar is S. S is a variable. Okay, start symbol for our grammar. S union these triplets of this form, Q, comma Z, comma Q dash, where Q and Q dash will take every value from the set of states Q. Capital Q is there in your push down automata. All those states appear in place of Q and Q dash. Okay, and this middle symbol Z, this belongs to the your tau, stack alphabet. Okay, middle symbol Z, it belongs to the stack alphabet, or in other words you can say that any element of V is the set of variable for the grammar. Any element of V is either the start symbol or an ordered triplet. These are nothing but these are the ordered triplet. Okay, these are the ordered triplet whose first and the last symbol are the states. Okay, and the middle symbol, the second one, is the push down symbol which is allowed to be pushed or popped from your stack. Okay, So the set of to define a grammar we need what are the variables. So what are the variables in the equivalent grammar? One is the start symbol S union all those triplets having this form Q, Z, Q dash, where Q and Q dash will take all values from your capital Q, which is the set of states in your corresponding push down automata, and Z is the symbol from the stack alphabet. Okay, then these see, if we define what are the variables in our context free grammar, then we need the production rules to write the production rules for the equivalent grammar. So the production rule is, first one is the, see, R1 is S production. S production means the production for the start symbol is given by this rule, where S derives Q naught and Z naught and Q. It simply means this, see, this first symbol of this triplet state fixed. Okay, Q naught, this is the initial state of your push down automata. Z naught is the initial symbol of your stack, and this Q will take all values from the capital Q. Capital Q contains all the states. Okay, let's suppose there are only two states, Q naught and Q1. So in place of this Q, once you have Q naught, another time you have Q1. Okay, so S productions will be S derives Q naught, Z naught, Q naught, and S derives Q naught, Z naught, Q1, because this last Q in the triplet, it will take all values from the capital Q, right? So given a push down automata, we have only these three types of production rules. Okay, one is the production rule for the start symbol. Okay, then if there is a production, there is a transition function in your push down automata of this type. Each move erasing a push down symbol means we are popping a element from the stack. Okay, every such move introduces a production rule of this type. Every such move introduces a production rule of this type. See, here we have delta is a transition function. We are on state Q. Okay, and then input symbol is A and top of the stack is Z. Then what we are doing here is we are removing this Z. We are popping this Z from the stack. See this epsilon. Now this Z is removed from the stack. So every move where we are erasing a push down symbol, we are popping a symbol from the stack. Every such move introduces a production like this, like where Q, this Q, this Q, Q, and this is the Q dash, this Q and Q dash. Z is, it comes in the middle and it drives the symbol A. Okay, so where we are erasing. Third one is, rule number 3 is, this was rule number 2. Rule number 3 is each move not erasing a push down symbol. Each move not erasing a push down symbol means we are either doing nothing with the stack, or we are pushing another symbol onto the stack. Either you push a new symbol onto the stack or you are doing nothing. Okay, but you are not erasing a push down symbol, right? So then we apply the rule number 3. Like in this rule number 3, delta Q A Z equal to Q1 Z1 Z2 up to some Z value M introduces this type of rules in transition function of your given push down automata actually introduces many productions of the form this Q, again see, of the form this Q Z Q dash. Now if you look at this, see this first Q, this comes here. Okay, this Z comes to the middle. Okay, and this Q dash will take all values. Okay, this Q dash will take all values from the capital Q, derives this A will come to this side. Okay, then these triplets, this Q, this is fixed, this Q, this will always start from Q1, and then Z1 Q2. Okay, Z1 Q2. Similarly, then from, because you are ending here at Q2, then again you start from Q2, Q2 Z2, this second push down symbol Z2, then Q3. This is will repeat for all the states up to this Zm and Qm, where Qm is last state, Zm is the last symbol in your push down automata, right? Where each of Q dash, see each of Q dash, Q2, Q3 up to Qm can be any state of your push down automata. Capital Q represent the all the states of your push down automata, right? So these two types of rules are only there, because when we write down the transition rules for the push down automata, we are either deleting, either popping a symbol from the stack, or we are inserting or not doing anything, means we are not erasing a symbol. So only these two types of rules, R2 and R3, these two types of rules are there, and by applying these two we can write down the equivalent production rules, right? And the start symbol productions are given by the rule number 1, and okay, rule number 2 and 3 gives the equivalent production rule for the every transition function, every transition rule of your finite automata, your push down automata, right? So let's see with the help of an example. See, while doing this conversion from a push down automata to an equivalent context free grammar, we only require these to remember these three rules. Okay, let's see. So this is one push down automata, right, given by A, and where the this symbol is this Q naught and Q2, this is capital Q. Okay, this is your capital Q set of states. This is your input alphabet, this is your tau stack alphabet, this is your transition function, initial state, Z naught is initial stack symbol, and we are written 5, means this is a this is your push down automata which accept by a empty stack. Okay, and these are the transition rules of your finite, your push down automata, right? So for example, first rule is an example of Q naught B Z naught, and you are going to Q naught Z naught. So it means we are inserting, okay, it means we are pushing something, a new another variable Z onto the stack. Okay, so here we can apply the rule number 2, here we can apply rule number 2. So we'll take one by one every transition of your push down automata and write down the equivalent production rule of the grammar, right? So let's see. So let's begin with, let us first define a grammar G. Let first define a grammar G. G is equal to your V again comma T comma P comma S. Okay, this is the equivalent context free grammar, where now we need to give what is variables, what is where V is equal to, we already said that. See, if you want to see the, I'll go to back. See, this S productions are given by a set of variables is given by S is a new variable which you introduce union these triplets Q, Z and Q dash, Q, Z and Q dash. So what we can do is, see, we have S is one variable, another rest are the triplets, triplets of form what? See this Q naught, Q naught, Q naught, then Q naught, Z naught and Q naught. Okay, Q naught, Z naught, Q naught. Another one is Q naught, Z naught, Q naught, Z naught and Q1. Okay, another one is Q naught, Z and Q naught. Another one is Q1 Z, Q1 comma Z comma Q1, like this. Okay, another one is your Q naught Z and Q1. Another one is Q1 Z naught, Q1 Z naught and Q naught. Another variable will be Q1 Z naught and Q1. Another variable will be Q1 Z Q1, and this is Z, Q1, this is Z and comma Q naught. Okay, so all combinations of Q naught, all combinations of Q naught, because see these positions are this position and this position, these position will take all the values from the state Q. Okay, we said that these variables are the triplets, in triplets where the first and the last symbol will take all values from the capital Q. Capital Q is nothing but it is the states, and the middle element will take the values from the stack alphabet. In our example, our stack alphabet contains only two symbols, Z and Z naught. Okay, Z and Z naught. So we have three different symbols, and these three different symbols we can achieve how many? 8 combinations are there. So accordingly there are these 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 variables. I put comma between these 8 variables. So these triplet, every triplet represent a one variable of the your grammar. Okay, every triplet will represent one variable of the grammar. So we now have defined what are the variables. Now we have to give S productions. Production rules are now productions are production rules of the grammar are, see, first we'll define the S production. S productions are defined by S derives. We have said that in a rule number 1 that Q naught is the fixed, Z naught is the initial value, and this last position will take all states. All state means in our automata we have how many states? We have 2 states. One state is Q naught, so one rule is this. Another rule is S derives. When we are writing the production rule for the your start symbol, then this is the rule Q naught, and then we have Q1, because this place will take all values from the capital Q. And capital Q is the set of states in the corresponding finite automata, right? Capital Q is the, so let me call this is production rule number 1, okay, this is production rule number 2, right? Production rule number 1 and production rule number 2. So these two are the productions of your start symbol, right? Accordingly, now we will take other rules. For example, let me take Q naught first transition of your automata, push down automata, and write down the rules accordingly. Okay, so let's see. Another rule is we'll take them one by one. So it is delta, and it is Q naught B and Z naught. Okay, Q naught B Z naught is equal to Q naught B Z naught is equal to Z and Z naught. Now which rule is applicable in this case? Here, because this is rule number 2, this is R3 will be applicable here. R3 will be applicable. R3 will be applicable. What is R3? R3 says, rule 3 says that when you are not erasing a input, when you are not erasing a symbol from the stack, okay, then your such type of transition will introduce many production of the form, like let's suppose, see, what we have to do is this Q naught will come here. So this Q naught, then this Z naught will go to this middle position, and then this third position is we call it Q dash, and Q dash will take all values. So Q dash will take one time it is Q naught, another time it is Q1, because there are only 2 states in this particular example. Okay, so this will take, this B will come here, this B will come here, this Q naught is your fixed value. Okay, then we have 2 values, Z and then Q naught, and then finally we have Q naught, we have your Z naught and Q1, again Q naught, because from where you are starting, this symbol, this place and this place, these two must be same. So similarly, another production can be Q naught, Z naught and Q naught. Okay, Q naught, Z naught, Q naught. Now this time what we are doing is P, B, this is Q naught, then we have Z, and then this is Q1. Because we are ending at Q1, we'll start from the same symbol Q1, then your again Z naught, and then this is Q naught. Okay, second rule. Third rule is now in place of this Q dash will take Q1. So it will be Q1 derives B, we have Q naught, then we have Z, we have Q naught, we have Z, Q naught, and then because we are ending at Q naught, we'll start with Q naught, and Z we end with Q1. And again we have another rule, because Q naught, Z naught, and this is Q1 derives what? B, because we are having Q naught, Z, Q naught here, and then we are Q naught, Z, Q naught. Q naught case is already considered, so it will be Q1, Q naught, Z, Q1, then it is Q1, Z naught and Q1. Now see, this all combinations are, now let me call this production rule number 3, this is production rule number 4, production rule number 5, and production rule number 6. Okay, let's take another rule from our finite push down automata. Second one, Q naught, where we are erasing, okay, where we are erasing a symbol. So another rule we can take is delta, we have Q naught empty and Z naught. We are doing what? We are staying at Q naught, and okay, in this case In this case, what we are doing, we are actually erasing a symbol from the push down automata, from the stack, okay, because Z naught is already there, and after this transition, this Z naught will be deleted, will be popped out from the stack. In that case, it will introduce a production rule of form. Which production rule? We have Q naught, we have Q naught, Z naught, we have Q naught, Z naught, and Q naught. We have Q naught, Z naught, and Q naught. It derives epsilon, and let me call this is a production rule number 7. Okay, you got my point. So here, which rule we have applied? R2 will be applicable in this case, and after we apply R2, our production comes like this. Okay, so P7, let me call this production rule number 7. So let us take another transition of your push down automata and write down the equivalent grammar production rules. Okay, so next production of our automata is delta. It is Q naught B and Z. Q naught B and Z is equal to, again we have Q naught Z and Z. So if you can see, it is again a case of R3. R3 rule means here we are inserting, we are pushing a new symbol onto the stack. Okay, R3 will be applied when you are not deleting, not erasing a symbol from the stack. Okay, when you are not erasing a symbol from the stack, then you apply the R3. So in this case, you again write the equivalent grammar production rules. So it will be Q naught, Z Q naught, because we have Z now, Q naught Z and Q naught. The last symbol in this triplet will take all values from Q, all value, and this symbol B comes to the right, and then Q naught Z Q naught. Again you simply Q naught Z Q naught like this, and then because we have stopped with Q naught Z and then Q naught Z and then Q naught, one symbol is this Q, this is Q, because we have started from Q naught, we will end here with Q naught. Another rule will be that we have Q naught Z and Q naught derives, again we have B here, we have Q naught Z, we have Q1, and because we have ended with Q1, so we'll start with Q1 Z and Q naught. One is this. Okay, now instead of this Q naught, I'll start with the Q1. So we have Q naught Z and Q1, Q naught Z and Q1, and here derives B. Here I have Q naught Z, Q naught first, and because I have started with, I will see Q naught Z and Q1. Okay, then similarly Q naught Z, here I have Q1, and then in this case we have here Q naught, then we have Z, then we have Q1. Okay, and because we have ended with Q1, we'll start with Q1 and Z and then Q1 like this. See, this last symbol, this particular symbol and this particular symbols are same, and this position will take all the values from the capital Q. Okay, so this is the case where we are not erasing a symbol from the push down automata. Okay, stack, right? So let's take and let me give a name to these also. So this is your push down production rule number 8, production rule number 9, production rule number 10, production rule number 11. Similarly, we'll take another one, delta. This is Q naught comma A comma Z. This is a rule in our push down automata, and then we are going to Q1 and head. So in this case, what we are having is, we are not erasing, we are not pushing a new symbol, but we are not erasing also. Okay, so again R3 will be applied. R3 will be applicable. All three rules is, it says that such type of transition will introduce many production rules of the form, these triplets like we define here. So it is Q naught, this Z comes to the middle. Okay, and this third position will take all values. So let me take first Q naught. Okay, first q naught derives, this a will come to the right side a, then this q1 is fixed. Okay, there is only one symbol which is z, and this q naught and this q naught, they must be same. Okay, then q naught, then we have z, we'll take another value which is q1, we have a to the right, we have q1 z, and now we have q1. So these two production rule, let me again give a number to them. This is P12 and this is P13. Okay, production rule number 12 and 13, right? So what else is remaining? That we have two more transitions of our automata, push down automata. One is q1 comma b comma z is equal to q1 comma epsilon. So this is again what we are doing, we are erasing a symbol. Okay, when we are erasing a symbol, then it simply says q1, z and q1 z and q1. We are actually erasing what? We are erasing b. Okay, so we can call this what is the production rule number? 13. Then we have 14. So this will be production rule number 14. Okay, then last one is delta. We have q1 comma a comma z naught is equal to q naught and z naught. Okay, now in this case also what we are doing, initially on the stack we have z naught. After this transition function we are still having z naught. We are not erasing any symbol. Not erasing any symbol means rule 3 will be applicable, and which says that the q1, this z naught come to the middle, last thing will take all values, so it will take 1 q0 derives, this a will go to this right side, then we have q naught and z naught and q naught. Okay, next time we have q1 z naught q1, it will take, now see this, now it is q1, earlier it was q naught. Okay, then it has a, then we have q naught, z naught and q1. So this is production rule number 15, this is production rule number 16. So see, we have now defined everything for our corresponding your context free grammar. We have defined what? We have defined set of variables v in the beginning. We have defined the production rules. S is the new start symbol. Okay, and the alphabet symbol remains same, that is a and b in this case. So you must write down the complete grammar in the form that we have defined v, we have defined t's are same. Okay, and then p, we have production rules, which has, in our case it is having 16 rules, and then s is a start symbol. So you need to write all these, right? So this is your a simple example to convert a given push down automata and write the equivalent grammar. Okay, so we can have let's suppose take some example. Let us try and some other example. You do it by yourself. Take any language. Let L is equal to, let some language L is equal to like this. Let's suppose we call it a raised to power m, b raised to power m, and c raised to power n, with m and n greater than equal to 1. Okay, design a PDA for this. Design a push down automata. For the above language. Okay, design a push down automata for the above language. Okay, for the above language, and then write the equivalent context free grammar such that L of G is equal to L of A, where A is your push down automata, G is your some context free grammar which you have written. Okay, so this is all about writing context free grammar for a given push down automata, right? So any queries you can ask. Okay, thank you.